Section 9.7, Taylor polynomials and approximations. Recall the mean value theorem. It guaranteed that there is some c on the interval from a to b such that the derivative at c is f of b minus f of a over b minus a. Now, you might recognize this as the instantaneous rate of change equals the average rate of change, which is also f prime at c is equal to the limit as x goes to c, that should be there, of f of x minus f of c over x minus c. This is the alternate form of the derivative that you know. Now this extends to f of x equals f of c plus f prime of c times x minus c. This is our point slope form. You might recognize f of x minus f of a equals f prime at a times x minus a. You can use any dummy variable we need. But if I go to this diagram here, notice I've got this function, okay? And on the closed interval from a to b, I have a point where the derivative, the slope of the tangent, equals the slope of the secant. Okay, that's what we're talking about with the mean value theorem. My function is continuous on the closed interval. It is differentiable on the open interval. If that's the case, there exists a c on the open interval from a to b such that the slope of the tangent line at c is equal to the slope of the secant line from a to b. Now, I can use that tangent line to approximate y values of our function. If you recall, when we were working with Euler's method, we did another way of approximating values of the function using our tangent line. We took our given y that we knew plus the slope times the change in x, which gave us the next y. Well, that's called using the idea of local linearity. This is the idea that you can use the equation of a tangent line to a function to approximate a function f near that x equals a. So f of x is approximated, very important, approximated by f at a plus f prime at a times x minus a. Again, point slope form of the line. This is called a linear approximation of the function at a. Obviously, I don't want to move very far away from a to use that tangent line as an approximation because you can see that the function diverges from that tangent line pretty quickly. However, what could I do to get a better approximation in the neighborhood of a? What if I used a quadratic or a cubic function for approximations? So this is the idea behind Taylor polynomials. That is using polynomial functions to approximate other elementary functions such as sine of x, e to the x, and natural log of x. It extends local linearity to local polynomiality. Made up word. Okay, that's a made-up term, so don't use that in other math classes. But anyway, if we understand locally linear using the tangent line, which is linear, to approximate y values, then using a polynomial to approximate y values of a function is what this is extending to. So local polynomiality is using a polynomial to approximate a function of f near a. What properties would a quadratic function have to have for it to be a good approximation of this function, let's say at a? Well, first of all, it has to have the same curve. It wouldn't make sense to use a quadratic that's doing this. It would have to pass through a f at a. It wouldn't make sense to use a quadratic over here. It would have to have the same tangent line at a. Okay, so now our quadratic function has to have the same curve, have to pass through the point a, f at a, and have the same tangent line. So you can see we need to be down here, which brings the fourth point. It has to have the same concavity. So the Taylor polynomial is the tool by which we extend local linearity. Have you ever wondered how your calculator knows how to calculate, say, y equals sine of 27 degrees? Well, on your calculator, let's graph in y1 sine of x. And let's graph. I want to have you look at something. We're going to look at y2 as, I'm going to actually use a different function for y2, and then I'm going to make this my y3. So you'll notice I've entered sine of x and x minus x cubed over 3 factorial, and then x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Let's look at what these functions are going to look like. Okay, here we go. Here is our sine function. We know what that looks like. Here comes our x minus x to the 3rd over 3 factorial. If you follow the bouncing ball, look at that. We can see that this converged along the sine function for that interval. I wonder how we could get a longer interval of convergence. Well, let's look at the next one. Ah, look at that one. Here we go. That is our x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Remember, 5, the positive x to the 5th means we go from low to high, and we have 1, 2, 3, 4, 5 directions. So that's pretty good. Look at that. We got convergence longer. I wonder how we could get a greater length of convergence. Well, what if we just take that function and then subtract off x to the 7th over 7 factorial? My degree term is going to have a negative coefficient, so we're going to go from high to low. So you can see our interval of convergence was even longer. So this brings us to a Taylor polynomial. The definition of the nth degree Taylor polynomial: if f has n derivatives at c, then the polynomial Pn of x, the nth derivative, n derivatives, is f of c plus the first derivative at c times x minus c plus the second derivative at c over 2 factorial times x minus c squared plus continuing the nth derivative at c over n factorial times x minus c to the n. That is called a Taylor polynomial for f at c. It's named after an English mathematician named Brooke Taylor. So remember that we talked about 0 factorial having to be defined as 1. Here is a reason. I'm going to have 0 factorial in the denominator. Notice that p sub n of x, my nth degree Taylor polynomial, that's what that means, the nth degree Taylor polynomial. Notice that this first term is actually the 0th derivative over 0 factorial times x minus c to the 0. Plus, there's our first derivative over 1 factorial times x minus c to the 1. Plus, there's my second derivative over 2 factorial times x minus c squared, and so forth. So the definition of my nth degree of a Maclaurin polynomial is exactly the same, but Maclaurin polynomials are centered at 0. And again, it's understood that we have over 0 factorial, over 1 factorial, and so forth. And this is named after an English mathematician named Colin Maclaurin. As we move through the examples for this section, let me explain the example. You pay full attention, and then at the end of the example, I'll give you time to write it down. So we are going to find the Maclaurin polynomial of degree 4 for f of x equals e to the 4x. Note n equals 4 means go to the 4th derivative, which means your polynomial will have 5 terms. So what are the things that we need to know? So we need the function. Maclaurin means we're centered at 0. So here is our function. F of x equals e to the 4x, and evaluated at 0 gives us 1. Now we need our first derivative. First derivative, evaluated at 0. Second derivative, evaluated at 0. Third derivative, evaluated at 0. Fourth derivative, evaluated at 0. Now we are ready to write our 4th degree Maclaurin polynomial. Our function is approximated. Very important. You must make sure that is an approximation. Our function is approximated by our fourth degree Maclaurin polynomial. So 1 over 0 factorial plus 4 times, this is x minus 0, so 4x over 1 factorial plus 16 over 2 factorial. Second derivative evaluated at 0 over 2 factorial times x squared, that's x minus 0 squared, plus third derivative over 3 factorial x cubed plus fourth derivative evaluated at 0 over 4 factorial x to the fourth. This is okay for the AP exam. This is what your polynomial becomes when all of those terms are simplified. Notice, my function is approximated by my polynomial. My polynomial equals this. Do not write plus dot, dot, dot. You'll lose a point. Pause the video and write down all of the information from this example. Find the Maclaurin polynomial of degree n equals 6 for f of x equals cosine x. Then use that 6th degree polynomial to approximate the value of cosine of 0.1. So 6th degree means I need 7 terms. So again, my 0th derivative is the function itself and evaluating it at Maclaurin polynomial 0. First derivative evaluated at 0. Second derivative evaluated at 0. Third derivative evaluated at 0. Fourth derivative evaluated at 0. Fifth derivative evaluated at 0. Sixth derivative evaluated at 0. You will notice I have a line here. That's because sine and cosine, when we find derivatives, they're cyclical. And after 4, you're back to the original thing. Just FYI, something you should know. And so I'm ready to set up my Maclaurin polynomial. My polynomial, my 6th degree polynomial is 1 plus 0 over 1 factorial x minus 1 over 2 factorial x squared plus 0 over 3 factorial x cubed plus 1 over 4 factorial x fourth plus 0 over 5 factorial x fifth minus 1 over 6 factorial x sixth. Now, what do you notice? These terms with 0 are dropping out, and look at that. So what we see here is, notice, all the degree terms are even, as are all the factorials. And to evaluate at 0.1, we're just going to take cosine of 0.1, approximate using our polynomial, which equals, substituting that in, gives us this value. Pause the video and write down all of the information from this example. Example 3, find the Taylor polynomial of degree n equals 4 for the function natural log of x at c equals 1. Then use the 4th degree Taylor polynomial to approximate the value of the natural log of 1.1. Well, let's remember, what are the things we need to do? We need to find the, well, remember, that is our 0th derivative. We need to find the first, second, third, and fourth derivatives of the natural log of x. And we need to evaluate each of these at 1. Show that notation. I don't know if you recognize the progression here, but 6 is 3 factorial. 2 is 2 factorial. 1 is 1 factorial. 1 is 0 factorial. So it's interesting that these are increasing by factorials. We know that the next one would have to be 4 factorial, and it would be positive if I were interested in that. Now we're going to write our 4th degree polynomial. 4th degree polynomial equals, there's our 0th degree, our 1st degree, our 2nd, 3rd, and 4th degree. Again, f prime at 1 over 1 factorial, f prime at 2 over 2 factorial, f prime at 3 over 3 factorial, f prime at 4 over 4 factorial. And simplified, we get this polynomial, and I can now use that to approximate the natural log of 1.1. natural log of 1.1 is approximated by the fourth degree polynomial, and that is this. It is very important that you have the proper notation. We're going to approximate the function value using our Taylor polynomial, and that value equals this. Pause the video and write down all of the information from this example. Now, an approximation is of little use if you have no idea of its accuracy. We can use the concept of the remainder to measure the accuracy of approximating a functional value f of x by the Taylor polynomial Pn of x. So let's remember, if we're approximating a value of a function, then there must be actually a remainder. And that brings us to something called Taylor's theorem, and is also known as the Lagrange error theorem, Lagrange form of the remainder. You have to know this, very important. Here's what the theorem says. If a function f is differentiable up through order n plus 1 in an interval I containing c, then for each x in that interval, there exists some number z, just a number, we don't know what, it's a dummy variable, between x and c such that my function is f at c plus f prime at c x minus c plus second derivative at c over 2 factorial x minus c squared, all the way up to the nth derivative evaluated at c over n factorial times x minus c to the n. This is our Taylor polynomial approximation plus the remainder. Now, what do I know about that remainder? Notice, by the way, we have used our function is. Okay, it is this Taylor polynomial plus whatever that remainder is. So our error is the remainder, and that is going to be found by the next derivative over n plus 1 factorial x minus c to the n plus 1. This is a mystery number z. We don't have to find it. But our Lagrange error bound is almost always used for sine and cosine because they're actually easier to use in this case. You might want to write this information down. Let's look at an example. The third Maclaurin polynomial. What does this tell us? Centered at 0. For sine of x is given by, there's my third degree polynomial, which is x minus x cubed over 3 factorial. We're going to use Taylor's theorem to approximate sine of 0.1 by finding our third degree Taylor polynomial and evaluating it at 0.1. See how all the words those symbols mean right there? Find the third degree Taylor polynomial and evaluate it at 0.1. Just those little symbols give you all those words. And then determine the accuracy of the approximation. Our third degree polynomial to be this. My sine of 0.1 is by the third degree polynomial at 0.1, which would be, this is given to me, this, which gives me 0.09983 repeating. So to use our Lagrange error bound, we now need to think about what's our remainder going to be. This is our approximation using our third degree Taylor polynomial. So that means we need our fourth derivative. So here's our 0th derivative, first derivative of sine, second derivative, third derivative, fourth derivative. Fourth derivative is back to sine itself. So we know that according to this theorem, that the remainder after the third derivative term is the fourth derivative evaluated at some mystery number z over 4 factorial times x to the fourth. And we know that our fourth derivative is sine of x. So sine of z over 4 factorial times x to the fourth. Now, what do we know about sine? Well, we know the value of sine cannot be greater than 1. In fact, we know that all values of sine fall between -1 and 1. And since we're near x equals 0.1, we can say with confidence then that the sine of our z, whatever z is less than 1. So now we can say that the remainder after my third degree Taylor polynomial is the sine of z over 4 factorial times x to the fourth, which is less than 1 over 4 factorial times x to the fourth, because sine of z is less than 1. Now, what we know is the remainder after my third degree polynomial is less than 1 over 4 factorial evaluated at 0.1 to the fourth, which is 0.000004166666666. So what this number means is that at x equals 0.1, this is how far off the Maclaurin polynomial value is from the actual value of the sine of 0.1. By the way, sine of 0.1, if you go to your calculator, it's going to give you this. What did we find as our approximation? 0.9983, repeating, 0.99833, and some others. So notice how far off. That's a pretty small error. Lagrange is cool. Taylor's theorem, Lagrange error bound, very cool. Pause the video and write down all the information from this example. Your TPs for section 9.7 are 1 through 4, 13, and 25. See you next time.